So last time, our I explained if you have an AC circuit, how can you calculate the power? Okay, consumed or generated by the different elements you have in the circuit. And as I told you in the complex domain, the power you are gonna calculate the complex power. First of all, I explained different formulas you can use to calculate the power based on what's available. If you have V and I, you have a formula for that. If you have I and Z, you have a formula for that. If you have V and Z, you have a formula for that. Okay, just you can use the easiest way. Okay, I explained several examples here, and you know when you calculate the power in the complex domain, this power has two parts: real part and imaginary part. The real part is actually the average of the active power, and the imaginary part, this is actually the peak value for the reactive power. And I told you also before that active power is good, but the reactive power is bad, okay? Because it's gonna increase the losses, and we tried our best to reduce the reactive power. Even if you look at the formula, yes. Yeah, so here, this is the good power, this is the active power, okay? You can see here we have cosine theta V minus theta I. And cosine theta V minus theta I, this part we call it power factor, okay? The PF, power factor. For sure, the best value for this one is 1, because this is the maximum value for cosine when it is 1. This should happen when theta V equal to theta I, okay? This the second part for the reactive power, as you see here, okay, the peak value for the reactive power is this part here. Same thing when theta V minus theta I equal to 0, in this case, this part equal to 0 because sine 0 is 0. Sine 0 is 0. So again, we always try to make theta V very close to theta I, okay, in order to maximize the good power and minimize the bad power here, okay? So you need to know how can you, because this will be in the final exam, okay? I told you one of the things, I will ask you to calculate the power, okay? I will give you very simple circuit. I will ask you to calculate the power. I will ask you to calculate the power factor, okay? Also, last lecture, I give you several ways to calculate the power factor. And today, I will give you very good example to understand, okay, why, number one, two things will explain in very good example we have here. I told you, when the power factor is very close to 1, that's what we want to do, right? That's very good. Because by doing that, we can reduce the losses. Okay? This is just verbal statement. I will show you an example here now, numerical, how this can happen. So I will show you at different values of power factor what happens. And for every value, I will calculate the losses. Just to confirm what I said right now, okay? You can see we can reduce the losses as we make power factor is very close to 1. Okay? And how can we make the power factor close to 1? We need to do something we call it power factor sometimes correction. You need to understand the concept of that. What do you mean by, if the power factor is low, I can add inductor or capacitor to increase it. Okay, that is the what we call power factor correction. Anyway, so let's come to this. Yeah, this example, this is a very simple example here. So as you see here in this example, we have a voltage source. This voltage source is in parallel to R, L, and C. Okay, I give you the value of R, the value of L, the value of C, and I give you this is the value of V here. So here again, similar to usually what we do, you have to convert this circuit from the time domain to the complex domain this way. Okay, this is R, this is J omega L, as we see here. But keep in mind, and this is the difference between this chapter and the previous chapter. Okay, keep in mind when I convert V from the time domain to the complex domain, look here, I'm going to use V maximum divided by 2, the square root of 2. That's V maximum. Okay. If you want to use only V maximum, I'm totally fine, but you need to use the correct formula, because I told you the formulas I give it to you should be for V maximum divided by square root of 2. That's what I did. Number one, you need to convert the voltage source here to the complex domain this way. Number two, R, when you convert R to the complex domain, it's going to be R. When you convert L to the complex domain, it should be G omega L. You have omega. Omega here is 5. Okay? L is given to you here. When you convert Z to the complex domain, should be 1 over G omega C. You can calculate it this way. Okay? This is the first step you have to do. After that, I want to calculate the power. I want to calculate the power here and the power here and the power here. Okay. So I'm asking you to calculate the total impedance. The total impedance you see from here. Also, I ask you to calculate the total power generated by the source. I will show you how can we do it in different ways. Okay. Let's start with the first part here. Okay. So you need, as I told you, I give you several formulas to calculate the power. You just use the simplest one. That's what I told you. So now for R, what do you need? What for R and L and C? What do you know? I know Z. I know Z here and Z here is Z here. So I know Z. Already also I know the voltage drop. Okay. If you want to make it difficult for yourself, okay, I have the voltage and have Z, I can calculate the current. And I have the current and the voltage, I can calculate the power. That's okay, but there is an easier way. There is already a formula. If you have the voltage and you have the impedance, you can calculate the power immediately. Okay, so again, it's not wrong. You can, it's correct, but I'm just, I'm asking. It's better for you to use the easiest way. Okay, and that's what I did here. So as you see here, guys, I want to calculate the power R. So the formula I can use here, the magnitude of the voltage square divided by ZR factors. Okay. But here, because R is just a resistance, it doesn't have an imaginary part. It does not have an imaginary part. Okay. That's why this one is 20 and it's going to stay 20. Okay. This square, you can, this base square divided by this value here. And then after that, you can, this is the power. I calculated here for sure. We don't have an imaginary power, okay, because this is a resistance. We don't have an imaginary power. And then, as you see here, the first part you have, I want to bring it to your attention because some students did this mistake in test 3. Okay? You know, once I did something result in complex domain, we transfer to the time domain. Okay. But this is only for the voltage and the current. Some students did it for the impedance. We don't, it doesn't make any sense if you have an impedance that has G and has a real value and you convert it to the, it doesn't make any sense to convert it to the time domain. Okay. Because in our case, the impedance has to be in a complex domain. Why? Why does it be complex domain? Because one part, the real part, gives you the amount of resistance you have. And the imaginary part tells you how much as the amount of capacity and inductance you have. What I'm saying? It doesn't make any sense to transfer it. Here, after you convert, after you get the power, you don't need to convert the power back to the time domain. Okay. What really once you calculate the power, I want to know what value here you have here, because this one gives you the average power we have. Also, I want to know how much we have here, because this value gives you the next value for the reactive power. You know what I'm saying? So once you calculate the power, for example, I calculate the power for this one, I'm gonna get 2 numbers, one real, one imaginary. So this, I'm just going to take this number. So don't forget to the final number. I just want to know how much. I want to know the average power. I want to know how much is the maximum value for the reactive power. So here you can see we only have active power and we have zero reactive power, which makes sense. Active power is coming from storage units, either capacitor and inductor. And here, because we don't have here inductor or capacitor here in this branch, that's why we don't have any reactive power, zero reactive power. Okay? If you come here to the inductor, I can repeat the calculations again. And you can see here we have zero active power, zero, because active power is related to resistive elements. Because this amount of power consumed by the load. And who's consuming power is the resistive load. But the capacitor or inductor load just store and release power. It does not consume power. That's why you can see here, this is the amount of reactive power, or this is the peak of the reactive power that is going to be produced by SL, as you see here, and we have zero active power. Same thing, I can repeat everything again here for Z. Okay. You can see here we have zero here active power, but we have negative 20 peak value for reactive power. Okay. Next question, I wanna find the total impedance here. Okay, that's easy because these three are in parallel, so you can calculate the total impedance here. Okay. Now, because here in the resistance, the impedance of the resistance should have only one real number. It doesn't have imaginary. Okay. For ZL alone, it has an imaginary number, but it doesn't have a real number. But if you take the total, it should have both. Because you can see here, the resistance we have or the load we have, it has a resistive and also it has an imaginary part. That's why if you take this total impedance, yeah, you can see here, if you can see how it has this resistive and imaginary part. Okay? The last part here, and that's very important, I want to calculate the power generated by the source. Okay? And I'm going to calculate in different ways. So one of the ways here I can calculate it is, look here, guys. I told you there is conservation of power. The power generated by the sources you have should equal to the power of the elements you have. I already calculated the power here in the complex domain. I calculated the power here. I calculated the power here. If I add them together, they should equal to this power. That's it. That's it. We have even the same thing in DC circuits. Okay? But here, I'm going to do it in the complex domain. Okay. So here, but we have the same thing also in this. So here, as you see, I can calculate the power of R, the power of L, the power of C. It's going to add them together, and this will give you the source power. Okay. So this is the total power we have. We can solve it in two other ways, and you can see we are going to get the same result. So the other way here is, okay, I can use V I asterisk. Okay, I already know V of the source that is given to me. So I want to find I need to find I. Okay? So I actually V divided by Z. Z is the total impedance, which is this one here. Total impedance we have. So I calculated the total current here, and then I have V. Okay, so V and I, by this way, I can calculate the power of the source. It should be the same thing. Okay. The other approach I can use, if you have the voltage and you have the total impedance here, I can say it's here is square divided by Z asterisk. So this value actually gives you the power of the equivalent resistance, which should equal to the power of the source. Okay? Anyway, so all of them should give you the same result. Any questions? Okay. This is the example I told you about, guys. This example actually is It is actually similar to our power at home. So you can see here we have generation or generator. This generator is generating power. Okay, this generator is not ideal. Inside the generator itself, it has some resistance and inductor this way because it's not ideal. Remember, if you go back to DC circuit, I told you some sources can be ideal. If the source is ideal, we don't have only R resistance in case of DC. But any inductor should be short circuit in case of DC. Anyway, so if the source is not ideal, so actually we have here R, like explained before. Okay. Same thing here, but in case of AC, because this is not ideal, inside the source itself should be, we have some resistance and inductor. Okay? This is a wire, this is a cable coming to your home, and same thing, this cable has a resistance and also this inductor. Keep in mind, I did not put this resistor or inductor. This is something natural. I hope if I can get rid of it. Any wire has a resistance, okay? There is no material or maybe gold or something like that, but all materials have resistance. You got what I'm saying? But in case of copper or some metals, the resistance is small, but it has a resistance. Okay? So anyway, so there's some resistance here. I wish if it doesn't, but this is Nietzsche. Okay. At home, this is at home. This is the power we have at home, 120 volt. Okay. And this is the load I have at home. The load is resistive RL and inductor L. Okay. And then I will solve the problem several times. Okay. I will solve it this way without making correction. So that's why you can see here in one of the scenarios we have here, I will consider adding capacitor here to make correction for the power factor. Is that okay? This question, but again, the importance of this question is just I want to show you by numbers how when number one, how when you increase the power factor, the losses will be less. Okay, because that's what I told you, but I want to show you the numbers. This number one. Number two, what is the meaning of power correction? That's what we do. So we're going to do some power correction to increase the power factor here by adding capacitor here, as you will see. So in the beginning, in the first scenario, we don't have a capacitor here. Okay? So let's see. Here I'm asking you, you need to find the power factor for the load. What is the power factor for the load? I give you here. See what I give you. Here I give you R, this R. I give you L, so you have R and L. Also, we have this R and this R and this L and this L, and they are equal. Okay, so I give them equal. Okay, and then you have the voltage at home. This voltage is 120. That's all what I have. Okay, so the first question here I'm asking you, you need to find the power factor for the load, the power consumed by the load, the power lost in the line, how much power we lost here and here in the connection here. Okay, because if we lose power, it's going to be here and here. Okay, so and for sure the power generated. So the total power generated equal to the power lost here plus the power consumed. So I want to calculate all of them, and then after that, I will repeat the same scenario again. This time I'm gonna make correction to the load to make the BDF higher. Sorry, the BF higher, the power factor higher. When you make the power factor higher, you will see, and then I want to compare numbers. I want to see what happens to the losses. Okay, you will see the losses here will be less. Anyway, let's start with the first scenario. How can you find the power factor for the load here? How can you do that? The easiest way, if you go to the last lecture, I give you 3 ways to find the power factor. If you have V and I, from V, that means you have theta V and theta I. You can calculate the power factor. That's case number 1. Case number 2, if you have the power here, the angle of the power is about theta V minus theta I. You can just take cosine of this power factor. Number 3, case number 3. If you have the impedance here, the angle of the impedance is actually theta P minus theta I. Okay, so maybe this is the easiest way for me. So here I calculated the impedance here, which is actually R plus J omega L. I have R here and J omega L here. Okay. After I calculated the impedance this way, I found this is the impedance, this is the value, and this is the angle here. So this angle is theta R. Makes sense? So now, if I want to calculate the current value for the power factor, so I have to take this is theta V minus theta I. So it should be 0.71, and it is lagging. Okay, lagging means lagging means this angle is positive. That means theta V is greater than theta I. It means I is lagging V. I is lagging V. Theta V minus theta I is positive. That means V is greater than I, or I is lagging V. Anyway, so here, this is the power factor. This is the current power factor I have right now, 0.71. Okay? It's not too good because you know the best value is 1 when it is 1. Okay? But anyway, I will go with it. Now, I want to calculate now how much power you will consume here, how much power you will lose, and the total power which is equal to the summation of 2. Okay? So let's start with the first one here. I already know the voltage. This is the voltage given to me, 120 volt. Okay? And then I know Z. So the easy way to do it is just use this formula here. This is divided by this. Okay. I have Z. I calculated the amount of power here for you. Okay? Okay, guys. So here, there's two parts here. This is for this part is for the amount of active power, and this part here is the amount of active power. Okay. They look equal, or they are equal. This is by action. They are equal. They are equal because I think cosine 45 is equal to sine 45. It's right. Anyway, because of 45 they should get it. Anyway, whatever it is. So now I found the power consumed in this case. Okay. And then after that, I want to calculate how much losses I have here. How much losses? Okay, to calculate the losses, I need to find, or the easy way, I can find the current, and I can find the total total impedance. Okay, so I can find the total impedance here. Okay, it's easy. The total impedance should equal R plus R, L plus L, and then so you can calculate it this way. Okay, you have this impedance and this impedance. It should be easy to calculate because they are equal. They are equal. Anyway, so I calculated ZL, they are equal. Okay, so for each one of them, this is R. It's given to me. This R is given to me. Yeah, 0.2. So R is given to me, and then J omega L. J omega L. Omega is given to me. L is given to me. Okay. So everything you have it here. Okay. So anyway, so after you calculate it, I find this is the impedance for this one or this one. They should equal because R is the same, L is the same. Okay, so this is the impedance. So the total impedance for both of them should be ZS plus ZL. Because in series is the total impedance. They are in series. Okay. So now, if I want to calculate how much power I lost, it has to be the total impedance. This is the easiest formula you can use. The total impedance I square. So all what I need to find I need to find the current I. How can you find the current I? Okay, I know already the voltage here, and I know Z. I know the voltage, and I know Z. And the current here is the same like the current here. It's the same like the current here. It's the same current. So if I can find the current here, it's the same current here. It's the same current here. Okay, that's what I did. So in order to calculate the current, should be V, which is 120 at home, divided by the load here. This load. I find the current. Now I just plug in here to find the losses. Okay. And this is the amount of losses we have here. Okay. Now, if I want to get the power as power of the source generated by the source, the power generated by the source should equal the power here plus the power here. This is the conservation of power. Okay, that's why I added these two together, and this is the final result. Okay, guys, I will summarize everything. Okay, but for now, when the power factor was 0.71, this is the result I got. This is the amount of power consumed by the load. This is the amount of power lost, and this is the amount of power the generator generated. Okay, I will repeat the same problem again after I correct the load. That's what I want to say. So that's what this is the purpose of this example to understand. Now I want to correct, not correct the load, correct the power factor. Okay, so I want to correct the power factor means I want to improve it. Instead of 0.7, I want to get it closer to 1. Okay? How can this time I will add capacitor here? I will add a capacitor here. Okay. So here I'm asking you the next part of the question. What value for the capacitor? Okay, I want to add a capacitor. So how big is this capacitor in order to reach the power factor 0.9? Okay, so here I want to add a capacitor to increase the power factor at the load from 0.7 to 0.9. How much capacitor? Okay, very simple. So here I don't know. I don't know the value of the capacitor. All what you have to do, I'm gonna try to calculate the power factor. Where I know the power factor, okay, I know everything except the value of the capacitor. So I will try to calculate the power factor, and then I will find what value for C for the capacitor I should use to make the power factor equal to 0.1. Sorry, 0.91, 0.9. Okay. So if I add here this capacitor in C in parallel, so here what is the total impedance here? Okay, because I told you the angle of the total impedance should be theta V minus theta I. Okay. Anyway, so here I will do the calculations here. Okay, I just normal calculation. I know everything except I don't know C here. Okay. After you do the calculation, as you see here, this is the final result. This is the real part, imaginary part. Okay. Again, yeah, I care about this angle because this angle is actually theta V minus theta I. Okay. Now, in order to find the value of this angle from this rectangular form, tan theta is equal to imaginary part divided by the real part. Okay. That's how you calculate the tan imaginary part divided by the real part. This is tan of the angle. Okay. This is the result. Tan of the angle should equal this value here. So what I want to do right now, guys, is I want to see. I have C here unknown. C is unknown. I can find tan of the angle. Why? Because I already know the power is cosine of the angle. Okay? You have the cosine of angle. You can calculate the angle, and then you calculate tan. Because this angle is actually theta V minus theta I. So what I will do right now, as you see here, okay, the power factor is 0.9, which should be cosine the angle. Okay? Given this one, so the angle here should be the inverse of cosine of 0.9, which is 25.884. So here and here, because it is lagging, so this angle should be positive. If it is leading, so it has to be negative. Okay? Because cosine will give you, that's what I told you last time. Cosine will give you this angle positive anyway. Because cosine for a positive value is positive, cosine of a negative value also positive. Okay, so that's why I need to give you another information. So here I told you it's given in the question. I want the power factor to be 0.9 and lagging. Lagging means the angle you are gonna calculate. Okay, take it as don't change it. It's positive. It has to be positive. Okay? And so yeah. So now I calculated the angle. This is the angle. So all what I'm gonna do here, I know the angle from the power factor. I'm gonna plug in here. Okay. The only thing that's unknown, from here I will calculate the value of C. Okay. So after I calculate the value of C, I found C is equal to 0.34 millifarad. Okay. That means if I do power correction to the load, by adding this capacitor here, I can increase the power factor from 0.7 to 0.9. Okay? Which is good, which shows reduce the loss. Okay? So next question here, I'm asking you, okay, can you find the value of the capacity that can reach the power factor 1? So 1 is better than 0.9, 0.9 is better than 0.7. So now I'm going to choose 3 cases. The first case I already calculated 0.7. I will show you when I calculate the losses for 0.8, and then I will show the best one at 1 when it is 1. Yeah, you can repeat the calculations I have here, but this time instead of using 0.9, I'm going to use 1. Okay, so that's what I did, and find this is the capacity. That means, guys, again, that's what I want to teach here, guys. What do you mean by power factor correction? I mean, I'm going to add here a capacitance, and this capacitance is going to, if I put a capacitance that's 0.34 millifarad, this capacitance can make the power factor 0.9. Okay. However, if I make the capacitance 0.66, okay, 66 millifarad, this is going to make it 1. Okay. Now I'm gonna repeat the first part of the question. I'm gonna repeat it, but now after adding these 2 capacitors. Okay? So now the load will be different. The load, it's gonna have this part. On top of this part, also it will have a capacitor here in parallel. So everything will be the same. The only difference is that when I calculated the load, when I calculate the impedance of the load, it was R in series with L. That's it. But now when I add a capacitor here, the impedance becomes this impedance of the capacitor in parallel to R and L. Okay? This is the only difference. After that, I'm not gonna so here. Anyway, I can go quickly here in the calculations. So again, I want to repeat everything again. I want to calculate how much power consumed here. I want to know how much are the losses and so on. So again, I found I found here the amount. What I did here again, you can solve it in different ways. Okay, you can repeat everything I did before, but this time you can take the impedance here, the capacitor here in parallel to R and L. You can do that, or I did here in a different way. I found the power here plus the power here. The power here, I calculate again. You can do it in different ways. So I calculated I here, current here. The current here equals the voltage divided by the impedance of the capacitor this way, and then I calculated the amount of power, okay, in the capacitor here, which is equal to this value VI asterisk, okay. And for the power here, it will be the same thing as before because nothing will change. It's going to be the same voltage. Voltage is the same, so I can use the old value. That's why I didn't calculate a new value here. I can use the old value, or you can yeah. So here for the losses, now the losses will be different. Why? Because by adding the capacitor here, the current will be different. Okay, that's why I need to calculate it again, because without what I did before, I need to calculate the current. Now by adding a capacitor here, now the load is going to be different. So now the current will be different. That's why here I need to calculate the total current here, as you see here, and then I calculated the losses. Okay. Anyway, I will choose a comparison because this is same thing here. You have to do it again for the 2 different values for the capacitor. So I just want to show you the conclusion here because this is the most important thing. Okay. So now, guys, I told you the first case here when the power factor was 0.71, and this without correction. This was the amount of losses, 727. And now when I added a capacitor here and I improved the power factor to 0.9, look how much reduction I had here. Okay? So instead of 727, now it became 449. Not only that, you can even generate less here I generated, amount of power generated was 430, 4,363. Look, reduction here as well. Okay. Now, if I use the capacitor that can make the power factor 1, look, I can even reduce it more. Even you can even generate less. Okay, guys. So let me tell you that this example again is confirming what I explained to you, but using numbers, numerical numbers. Okay. Number 1, this is the effect of reactive power. Okay? Because keep in mind, when the power factor equal to 1, what it means power factor equal to 1? That means what it means. Why the power factor does not equal 1? Sorry?
Not in phase.
Yes. Because theta D and theta I, they are not in phase. Why they are not in phase? Because if the loop is only resistive, it will be in phase. But because you have inductance for capacitor, it's not going to be in phase. Okay? So what happens here is that it's like when I added this capacitor here, the capacitance is going to cancel the impact of the inductor. And now it's like the total impedance now becomes only resistive. That's why now the power factor becomes 1. They cancel each other. Okay? This is the meaning of it. Okay, guys. Any questions? I think that's enough for this one. Any questions here about this part? Because this is completely different from DC circuits. Okay. So again, in case of AC circuit, for power, we have 2 types of power. We have active power, which is good, and we have reactive power, which is bad, because it increases the losses. Okay. And we have something we call power factor. The power factor is gonna tell me, the power factor, if I can bring it to 1, that means you can minimize the losses, which is good. Okay, you can minimize the losses and maximize the active power, because it's a useful power. Okay, because it's not going to benefit anybody. Just transmit power to the source and then get power from the source. Transmit power to the source, get power. That's how reactive power is. Anyways, the last part here I want to explain is about maximum power transfer theory in DC circuit and in AC circuit. Okay? There is a proof here, so just don't care about the proof. I just wanna show you, because I already explained it in case of DC circuit. I want to show you how it is different in case of AC sources. I think there is summary here. Yeah, this is the summary. So don't worry about the proofs here. This is the summary. If you remember, and this will be, I told you, this is one of the topics you need to study. Okay, for DC circuit, not AC circuit, but anyway. So for DC circuit, as I told you guys, if you have a circuit, okay, and this circuit has R7 and V7, and we have a load here, okay. So if you have something, if you have a circuit like this one, I'm very specific. If you have a circuit something like that one, you have a voltage source, resistance, and then load here. Here is the load, okay. So in this case, in order to maximize the power transfer from the source to the load, so the value of the load should equal to R7. So this one should equal to this value here. I think this was one of the question in one of the tests. Number 2, at this time, the maximum power in this here, if you make the load resistance equal to R7, so they are equal. Okay. In this case, the maximum power is actually V7 squared, the source is squared, divided by 4 times any one of them, because they are equal. R7 or RL, they are equal, any one of them. This is in case of AC circuit. Okay. And I told you, if your circuit doesn't look like that, you have a different circuit. Okay. And I think this was in the question in the test. Okay. If you have a different circuit, and I ask you to find the maximum the value of the load resistance for maximum power transfer. So easily you need to calculate this Thevenin for the circuit. Okay, I will give you example on this one hopefully after I finish this chapter. Okay, but if you have a circuit, this can be this R7, this can be the Thevenin of any circuit. Okay? But anyway, so this is in case of DC. Okay, I wanna. Okay, what about in case of EC? How these things are different? Okay? It's almost the same, but there is a very small difference. The first thing here, here because we work in the complex domain here, the value ZL, the impedance of the load should equal Z7, but asterisk. This is the only difference, okay? Here it has to be asterisk. So ZL should equal Z7 asterisk. Okay? And the maximum power, the amount of power here should equal to V7 square, the magnitude of this source squared divided by R6. Okay? I think I have an example here. I can go through it quickly before. Here, so let's for example go through this example. Here, this is a load I have, okay, and this is I told you we have here impedance here, and we have V7 here. This is V7. This is impedance, and this is the load I have. I think I'm asking you here in order, what should be the value of what should be the value of R and the element I want to add here. This element should be capacitor or inductor, and what is the value of this element? What is the value of R for maximum power transfer? Okay, so here this impedance ZS is actually RS plus J omega L. This impedance here, okay, which equals this value. You already know from what I explained here, for maximum power transfer, the impedance here is equal to the impedance here, but here this should be asterisk. Okay, that's what I did. So I have this impedance is given to me, but this one is not given to me. Okay? So yeah, that's why I'm gonna take the asterisk. That means the impedance of this part here should equal to this value for maximum power transfer, okay, which is ZS asterisk. Now, what I will do now, or look here, something like that. Okay? This is the part that doesn't have G. This one is actually resistance. This one, because it's negative G, this part is capacitor, negative G. Anyway, so the negative sign here means it should be capacitor, okay? Because in capacitor 1 over G omega C, if you multiply G, you can take this G up, it has to be minus G. This, okay? Anyway, so now, because I don't know the values C and L, I have two unknowns now. This R and Z and C. Okay. Anyway, the total impedance has to be this R in parallel to this C, as you see. Okay. So if you just do the calculation, this is the amount of impedance I should have. I have two unknowns, R and C. Okay. So this is the amount of impedance. This impedance has to, for maximum power transfer, has to equal to this one. That means the first part here has to equal to 5. And the second part here has to be equal to 10. Okay? And now you have two unknowns, two equations, you can solve them. Okay. So this part here equal to 5, this part here equal to 10. Anyway, so now I can solve the two equations, I get what is C. Now I think the second part here I'm asking you to find the maximum power transfer. Okay, in this scenario. So you can actually simply you can use this formula. Just you can do the calculation similar to what I explained to you for any circuit. Maybe it's easier. You can just use this formula. Maybe it's easier. Or you have here a voltage. You have voltage. You have two resistors. So you can actually find the voltage, and then you can find the current. Once you have the current and you have Z, you can calculate the power. So here what I'm doing here, you can just calculate the power because you have V, you have Z and Z. You can get the current. Once I have the current and Z here, I can calculate the power here. Or if you remember this formula, you can just use it. Both of them should give you the same result. Anyway, the last thing here, and I may not want to spend much time on it, is actually the power superposition theorem, but this is for power superposition. Or I already explained superposition in case of DC and AC, voltage and current. I explained last chapter, but this time for power. So there is a proof here. You can just, this proof just for you, but the conclusion of the proof is, yeah, there is a proof here. Just this will not be in exam, but let me tell you the conclusion here. The conclusion is the conclusion is the average power received by a load from several sinusoidal sources with different frequencies. So if I have multiple sources with different frequencies, okay? So the average power, only the average power received by the load should equal to the summation. So for example, if I wanna calculate the average power, and I have two sources, as you see here, two sources, but these sources should have different frequencies. Okay, so I can keep one and remove the other one, and then calculate what is the power here, and then I can do keep this one, remove this one, similar to. But again, this is only true for average power, and this is only true when you have different frequencies. Okay, same frequency is not gonna work because it has a proof here. So if I show you this example quickly, this example here. So again, I want to calculate the power here, I guess. So the way you can calculate it, I'm from this circuit, I can make two different circuits as you see here. I can cancel this one because it is a current source, it has to be off. Okay. And then now I can calculate how much power we have here. Same thing after that. You have here a current source. This voltage source, I'm gonna make it short circuit, and then I can calculate how much power I have here. And then I can average power here, average power, add them together. But this way you can get the total average power. Okay. Anyway, any questions here? So that's what I did. So for the first circuit here, in order to calculate the average power here, I can divide VS by the total resistance, as you see here. Once you have the current and you have the impedance here, okay, you can simply sorry, I want to calculate the power here in R, not this one. So here, once you have R and you have the amount of current, you can easily calculate the first component of the power. I can do the same thing here. Once I know I and I have R, I can also calculate. You can do the same thing, by the way, for the inductor. But here in this question, I'm asking you, what is the average power here in R? Or if I do it for the, I don't need to do it for the inductor because the average power for inductor is 0. I don't need to calculate it. You get what I'm saying? Average power for inductor and capacitor is 0. Okay? I don't need to calculate. That's why here I ask you to calculate for the resistance. Again, once you have the first power, second power, I can add them together to get final power. Again, this is very similar to what we did before, but here in case of here, it is very restrictive compared to what we had before. Very restrictive because you can use it only for average power. Number two, you can use it only for when frequencies are different. I think that's enough. Maybe I want to go through the topics. Here I told you guys that the exam will have these topics. Number one, I will give you a DC circuit, then I will ask you, can you give me Stephen and Norton equivalent of this circuit as seen by the load? This number one. Number two, I will give you a DC circuit. This circuit can have current sources, it can have voltage sources, It can have dependent or independent, whatever it is. So you have a certain circuit here, something like that. And then, for example, you have here RL. Okay. So the first thing here, I will ask you to find Thevenin and Norton for this circuit. Okay. Then after you find Thevenin and Norton here, so that means you need to find R Thevenin, P Thevenin, and then RL. And also, if I ask you for Norton or both, okay, it should be here I Norton, R Norton, and then you have here RL. So all what you have to do, you have to find the value of P7 and R7, okay? And as you know, R7 is actually equal to R Norton. I will try to give you one example to just finish, but let me now what you then if I have time, because I know still some students don't know how to calculate Thevenin and Norton, and it's so bad because I think I think Thevenin and Norton one example I teach you again. Okay, so I will try to give you one example on it. Then after that, I'm asking you what is the value of the load to maximize power transfer. So here you can use R7 and then you have here RM. I have just to give you the formula right now. Number one, for the maximum power transfer, RL has to equal to R7. Okay. Number two, what is the amount of power? So the amount of power in this case, for sure you can calculate it if you want, but you already have a formula. But if you forget the formula, you can calculate it. How can you calculate it? You can find the current. You can say R equal V7 divided by RL plus R7, okay? And then I square, and then the power here should equal to I square RL. Okay? So as you know, so DC circuits, in order, as I explained before, what resistance R, this resistance R has current I and the voltage V. You can calculate the power in three different ways. I can say power equal to I times V, or equal to I square R, or V squared divided by R. So whatever you use, you should get the same result. Okay? But there is a formula. I think the formula is V7 squared divided by 4RL, something like that. Okay, there's a formula you can just use. So again, if I give you a DC circuit this way, okay, you need to know how, and you already, some student contacted me. Okay, so what examples you need? Okay, the examples I explained in the lectures. How can you calculate R7 and P7? If you go back to the chapter, I will try. Hopefully, I can find some time to give you to solve one problem. But if you study the examples you have here, and again, all lectures are recorded. If you can go back to these lectures if you want, and you can see how I explained it. If you understand the examples you have, you should be the final exam will be easier than these examples. Okay. So this is, I think, this is the first. The second one, I'm going to give you a DC circuit with dependent and independent sources, and then I will ask you to apply mesh current or voltage nodal. I think that's very easy. We did it at the very beginning of this course. You need to know how can you apply mesh current and voltage nodal, okay? And the circuit can have like dependent or independent sources. Also, you need to find the power generated by sources and consumed by resistance. What I mean here, what I mean. Okay. For example, if you have here a voltage source like 5 volt, okay, and then you have here resistance R1, resistance R2, for example, something like that, resistance R3. Okay. So after you do the analysis using mesh or using mesh or voltage nodal, you can know for every, you can know for every source, you can know the voltage and the current. You can know the voltage or the current. You can know the voltage or the current. So all what you have to do, number one, you need to find the power consumed. Okay? Power consumed by each resistance. For example, for R1, again, you can use the easiest way, guys. So for example, if I ask you to do mesh, in case of mesh, mesh is gonna get you current. So I can use I squared times R1. But if it is voltage nodal or so voltage nodal, you are going to have the voltage. So in this case, you can use V squared divided by R. Okay. So anyway, so here, this is the amount of power for R1. For R2, amount of power is actually I here, I2 here. So I2 square R2. For R3, it equals to I3 squared divided by times R3. Okay. So this is actually the amount of power consumed, equal to the power here plus the power here plus the power here. Okay? If you for the power generated by the source, for example, if you have one source here, it should be actually 5 times R. Whatever the value here, 5 times R. Okay? If this source, if you may have another source, for example, if you not mention the function, if you have another, so the power generated by all sources is equal to the power consumed by all resistance. What I'm saying? So if you have two sources, for example, one current, one voltage, so yes, I have here I, and you need to find V, the voltage here V, and then this power here, I have to add V times I. So here I have to add the power here and the power here. The total power generated by all sources should equal to the total power consumed by all resistors. Right? Because this is conservation of power. This should be true in case of DC circuit or AC circuits as well. Okay? So here you need, in order to do well in this question, you need to practice on if you have a circuit with dependent and independent sources, you already have many examples. How can you use mesh? How can you mesh approach or the voltage nodal approach? Okay, should be easy. The second one, the next one here, I will give you an op-amp circuit and then DC, not AC. So you are not going to have capacitor or inductor, just resistor. And then I will ask you to analyze. One more very important thing today. Again, you also have many examples here, but the most important thing you should understand, guys, as I said, only in addition to Kirchhoff current law, Kirchhoff voltage law, all of these things, Ohm's law, there are also two important things we are using when we do this analysis. Okay, for example, here. Okay. So the first, in addition to Ohm's law, Kirchhoff current law, Kirchhoff voltage law, in addition to these ones, there are two more things we use. Number one here, V1 should equal to V2. V1 should equal to V2. And usually, V2 is given to you, and you are going to use it to calculate V1. Usually. Okay? So usually, you have this voltage, and you make it equal to this voltage. Okay? This is the first thing you can use. Second thing you can use is actually I1 should equal I2 equal to 0. I1 is the current here, and the current here, I2 is equal to 0. The current. Okay. Because of that, I can say, if you apply Kirchhoff current law here, if you apply Kirchhoff current here, so this I is equal to this I. For sure plus 0, because nothing will come here. Nothing will enter here. So this one equal to this one. And because of that, you can get some relations. For example, if you have here input, okay, so I can say V input minus 0 divided by R2, which is this current here, is equal to here V input minus V output divided by R1. Okay. This one for inverting amplifier. Again, for this chapter, you don't need to memorize. I will not ask you to draw a circuit for inverting amplifier, non-inverting amplifier, the other circuit. Okay, I will only give you a circuit, and then I will ask you to calculate to do analysis for this circuit. Okay. You don't need to memorize inverting or non-inverting or the different circuits you need. The next thing here, it will be similar to the test number 3. I will give you AC circuit, and then I will ask you to find the current and voltage of the elements you have. So again, similar to what we did in last chapter, number 1, you have to convert the circuit from the time domain to the complex domain. Okay. Number 2, after that, as I explained, you have many examples in the previous chapter. You can just, if you understand this example, I'm sure. Also, I posted the solution of test 3. The final exam will be easier than the examples you have. Okay. So here you can calculate. After that, after you convert to the complex domain, you can use the theorem we used before, like Kirchhoff current law, Kirchhoff voltage law, everything we used before. You can use it to calculate the current with the voltage in the complex domain, and then you have to convert it to the time domain. Okay, as we explained. There is something really very important, guys. Please. For example, here, when I ask you guys, if I give you a circuit like this one, and then I ask you, for example, here you have R1, R2, R3, you have here IS. If I ask you to give me Norton 7 for this circuit, I found some students are telling me, give me some magic numbers. How I grade it? Okay, for example, give me, yeah, V7 equals 3 times 2 divided by equal, whatever. How I got these numbers? What if this number is wrong? For example, I will give you 0. What else I can do? So the way you have to do it, that's why you need guys, for 7 and Norton, you need to draw the circuit. Okay, for example, here, because you are gonna open. So for example, if you're gonna calculate V7, so it has to be, I'm gonna calculate it for this circuit. You need to do the circuit here. Just I want to understand what you are doing. Just you are not just picking some random numbers. Okay, you open the circuit and then you need to find the voltage here. Okay? And at least start with this one, and then you show me how you did it. Okay? Same thing if you want to calculate like if you want to calculate like R7 from here. You need to draw the circuit. Show me. You are gonna open this one. You are gonna make this one short circuit, and then if you look from here, I will find R2 is in parallel to R1 plus R2. I found some students don't do that. Just give me some numbers. 3 plus 2 plus whatever. Don't even show me how you did this calculation. So very important for R7 or for 7 or Norton, you need to draw this circuit. The last I think here I will. There will be a question on transformer. We did not teach a lot in transformers, but I can tell you there is one example. The test will be easier even than this example. You need to understand. Yeah, here. Yeah, here in this example, I give you this example here. So it will be easier in this example, but if you understand this example here, it will be something like this one. So here I will give you the ratio of N1 and N2, and because of this ratio, you can already know the ratio of the current. Very important. So once you have this ratio N1 and N2, you can know the ratio of the voltage and also the ratio of the current. Okay. That's why if you have the current in one side, it's very easy to get the current in the second one. But you already have a relation. Okay? So if I know the voltage here, I can easily get the voltage here because there is a relation. If I know the current on this side, I can easily get the current on this side. If one of them is known, you can get the other one. Okay? So it will be similar. You need to understand this example. It will be even easier than the last thing, I will give you a very simple AC circuit. I will ask you to calculate the complex power. So I explained and also to only find the power factor. Okay. You have a lot of examples. You have different formulas I give to you. Okay. To calculate the complex power and also the power factor. Because we have some time, which part do you think that I have if you want to need to explain one if which part do you think I should give you example on this one here, Steven and Norton, or you are okay on all of them?
Did you do the last one?
Last one? Okay. I'm just did it, but that's okay. Okay, let me remember. I want to do for a different problem than what we have here. Okay, so I'm trying to, for example, I don't have the number of. Okay, for I want to do it. I want to do it for example. I just want to give you different example. I don't want to repeat what I said here. That's why maybe I'm gonna go to the question of. Maybe I'm gonna give some random numbers. So maybe I'm gonna try to solve.
Oh, I have this. I just want to. So I have to do calculation.
Yeah, here I didn't ask you to calculate the power, but I asked you to calculate the voltage. So for example, here is if I calculate the power, so here we have R, here we have C, and also here we have L is here. Okay. So for example, if I want to calculate the power, okay, I give you V. V here is equal 1000 cosine 100 C plus 50. Okay. So the first thing you have to convert this one from the complex to from the time domain to the complex. Yes. The voltage source should be 1000 divided by square root of 2, and the angle here is 10. And then R will be the same like R, and then we have the capacitor, then have CC, which is equal to 1 J omega C. And then here for the inductor, I have Z L, which is equal G omega L. Okay, so I remember I give you the value of L omega. So we have omega here, which is 100. So omega here is equal to 100. L, I give you C, farad, and L is actually 10. By using these values, you can easily calculate ZC. So ZC should equal to 100 G, and ZL is equal to 200 G, and then R, the R is the same value of R, which is 200. Okay. So now if I want to calculate the power of the source here, so the first thing you can do it in two different ways. If I want to calculate the power of the source, number one, you can find the current if you want. Okay, so I can say here if you divide V divided by Z equivalent, this should give you the current. Okay. V is actually 100 divided by square root of 2 with angle 10. Okay. The equivalent resistance is actually R plus ZL plus ZC. Okay. So you need to convert this one from the rectangular form to the complex to the which is actually the polar. So x will be 1,000 divided by 2 root of 2 is 110, which is divided by the total resistance, which is 2 determine angle 26. By this way, you can calculate the current. Once you have the current, can you get the power here? Can you get the power here? Yes. The power here should act equal to V R asterisk. So I'm going to use the same value for V. But for I, after you calculate I, you need to get I asterisk. And in I asterisk, assuming, for example, I was something like, for example, 5 with angle 20, any number, okay? So I asterisk should be 5 with angle negative 20. So this is how can you calculate the power here. Okay? To calculate the power of each element, to calculate the power of each element, so actually I think because you already have the current, okay, there are we have different formulas, okay? So one formula is actually VI asterisk, if you know the voltage element, and I asterisk, also it can be I square times Z, or it can be V square divided by Z prime. So whatever available for you, but in this case, because I is available for me, okay? So for I here, I need to get the magnitude of I, which is 5. So here it should be 5 square, magnitude of I, which is 5, should be 5 squared times the value of Z. So here Z is R, it will give you the power here, plus the power here, plus the power here, should equal to the power. Okay. For the power factor, assuming this is the load, so assuming here, this is the load here has a resistance and then inductor and then capacitor. Assuming this is the load here, if I want to calculate the power factor for this one here, again, there are different ways you can do it. Okay. The easiest way, because you already have Z here. Okay. You already calculated Z. What is Z? That's what I'm looking for, 26, because 26 is actually theta V minus theta I. So all what you have to do, just take this angle, cosine this angle. That's it. And if the angle is positive, you have to tell me it is lagging. If the angle is negative, you have to tell me it is leading. That's it. Okay? This is one way to do it. There is another way, because you already know the voltage here. The voltage here is equal to the voltage here, the same voltage. That means you already have theta V. And because you calculated the current here, you have this. That's why you know theta I. So if you already have the voltage and have I, that means I have theta V and theta I. So the power factor should be cosine theta V minus theta I. That's it. Okay. But again, because this one will be positive anyway. So you have to tell me if this value here is a positive, you have to tell me it is lagging. That means I is lagging V. Okay? Or if it is negative, you have to tell me it is leading. Okay? One more thing. If you know the total power here, if I know the total power here, this power should have a magnitude and angle. This angle is actually theta V minus theta I. I can just take this angle theta V minus theta I and then take the cosine. Look, you have different ways you can do it, whatever easy. Anything else? Yes.
What's the difference between Z and Z prime? Z star?
Yeah. So, you know, if you have a complex number, for example, Z should equal 3 plus 5G. This is a complex number, regardless if it's Z or not. Okay. If you have a complex number, or this is in the rectangular form, or you have, for example, 100 with angle 20. Okay. So you can calculate what we put the conjugate. Conjugate of this number. when you calculate the conjugate of this number should be 3 minus 5. So here you have, if this one is positive, you make it negative. If it's negative, you make it positive. Okay? So this number, this complex number is a conjugate of this complex number. Okay? Same thing here. If this one here, so it should be 100 with negative. If this one is positive, make it negative. Negative, make it positive. This number is a conjugate for this number. That means if you multiply these two numbers together, you are gonna have only real part. This is the meaning of conjugate. Okay, so you are gonna have only a real part. There is no imaginary multiplication together. Is that okay? So here, when I say z asterisk or I asterisk or d asterisk, I mean once you have z or I or b, you need to calculate the conjugate of this number should be actually z asterisk or I asterisk or b. Okay, so I don't want you to worry. Just to do your final exam. I hope so. So just do it this. The final exam should be easy. And when I had vision, I could get to come over and tell you. So just do this, you will. Okay, and then you will. I actually. If you do not take your test, I have it here.
Actually, zoo is. Yeah, well, right. Oh, it's so nice. There we go.
I was just. I have to wait for him to get back.
Yeah.
Yes, you get back. Williams. Williams. Brackets. Brackets. You have my backpack. Okay. Holland. Holland. Bastard. Donald, Clark, Carol, William, Charles Scott, Patrick Clement, Patrick Clement, Webb, Abram, Abdullah, Kim, Ibn Sunni, Linda, Lisa, Nicholas, yes, guys. How to meet with these students? Ethan, Sauler, Paige, Grace, Morris, Marvin, Lawrence, Yes, look here. I should use this formula, yes, for this circuit. Okay. This circuit is not like this one. Okay, right, so I have to make it like it. How? By taking a notebook for this part. Right. I take a notebook for this part. So then I'm asking you, where is my notebook?
So the north for this circuit is the same as the 4 times 0, correct? For the circuit.
What? You need to calculate. That's what I'm saying is.
I just said, I mean, that's what I calculated here.
Yeah.
Was my current for t is less than 0. When I looked at your exam, which is very similar to one I did. I did not have, I'll go look at it again, but I didn't see where it said. Maybe I just so skipped it.
That's what I'm saying then. Okay, let me, this very important for fine.
Yeah.
Okay, look. You calculate, you put it here correctly.
Okay.
But I don't know how you got it. Because I'm saying the way you have to do it is, I have here VS, I have here R1, and then I have here R2. Then you open the circuit this way,
Yeah.
okay? And then for Norton,
Like this, right?
yeah, but it's okay. That's why I give you the
Yeah.
mark for all.
I understand.
So you get me the circuit, I will look here, I found this is all. Correct, that's good. But you didn't do that for Norton, right? So for Norton, you have to make, and then I make a short circuit, and then I wanna find I go to. Yes, yes?
Yep.
And then this one will cancel this one, the short circuit will cancel it.
Yep.
So actually, I Norton should equal VS multiplied by something.
Okay,
Which is the same thing like here.
I just didn't write it as.
And I just found you put a digit number into the, yeah,
Okay,
but where you got it?
so
You got what I'm saying?
to make this correct, I would have to draw this circuit and then just say, wait, but this is I or not. Is it's still VS over? It's.
Even here, man, how you came up with this number? This, you also need to do a circuit here because yes. You have to tell me, you have R1.
I think what I did, I didn't draw the circuit, and when I was looking at it, I just made the short circuit. That's my fault.
Yeah, because you need to show me, because I say, so now you have R1, you are gonna cancel this one because the switch is open.
Yes.
And now you need to show me the inductor here is actually short circuit. Okay, and by this way, the current I have here, I should equal VS divided by R1.
Alright.
You didn't give me the circuit, but at least you give me a formula. But for Norton, you didn't draw a circuit, you didn't even give me a formula. So you got to say,
Okay.
this was.
I just, like, I understand I didn't draw the circuit, but why?
And even you didn't give me a formula. You don't know how.
The formula is the same here.
You didn't tell me that.
Okay,
So I guess you didn't tell me that. You just tell me if T is greater than 0, I is okay for 0.
Okay.
I said? Anything else?
no, I mean, that's fine.
I can give you 1 point. It's not big deal for me.
I just wanted to understand where, how.
Man, I'm not grading the last numbers.
Oh, I know.
I'm grading your understanding,
Yeah,
right?
so I just want to understand what step I'm in.
Yeah,
That's all.
So you didn't, here, at least you give me a formula. Okay?
Yeah.
You didn't do a circuit. I did not penalize you for that, but at least you did here
Yeah.
in Norton. You did not, you said just say T here. I can give you 1 point, that's correct.
Okay.
Okay, so if you want, I can give you 1 point, okay? Anything
I
else?
can send you an email. That's my only question.
Okay, that's okay, send me, I mean, to remind me, I will give you 1 point. Okay?
Thank
But
you.
in the future, man, just show me, don't just give me magic numbers.
Okay.
Show me. Because I don't care about the final numbers.
Right.
I only care about your understanding the steps. It's up. So anyway, send me an email and then I will tell you.
Just had a question. I don't know what you mentioned.
Okay, so
I was just wondering if you did or didn't.
I did not say in the very beginning of the course I will do that. But honestly, what I usually, just to do your bit with the final exam, what usually I do, I add everything together, okay? And then I target a certain GPA for the whole class, okay? For example, 2.7, 2.8, 2.4, whatever it is. I target a certain GPA, and then I curve. So So that's why I'm saying if you are doing better than the average of the class, you are gonna be okay. Even if the whole class doing poorly, you get what I'm saying? So as long as you are better than the other ones, you should be okay because I will post it.
Yeah, I was just,
But I did not say in the beginning of the class, I will it once. But again, just do your best.
yeah, it's 40% of our grades. It's what happens. So,
40% for what?
for the final thing, correct? It's-
I need to know, but I just put it in the beginning. But again, the final will not be difficult, it will be very simple, simple. Just do this one. Oh, you're going to go that for that. Oh, I think I did something more than I didn't.